my God. Wow, I thought I had a plan, and now it's all just gone. I'm so excited to have Roger Penrose here. Roger Penrose, I know, let's just... I was going to give a semi-formal introduction, but I'm not going to. Roger, as many of you know, is one of the most creative mathematical minds of our time and has taught us so many things and is really just an exemplar of the idea of mathematical originality. And we're going to talk about that, creativity and originality in mathematics. When I was a student, I don't know if I ever told you this before I discovered physics and math, I thought physicists memorized things. Oh, look, he's laughing. It's good. Good sign. Because physicists have the worst memories, and Roger and I tonight were talking about biology and how I couldn't keep track of all of those names and the nomenclature. And physicists notoriously have terrible memories. It's all about being able to derive something from the simplest original sentence, right? And I'd say Roger has taught us a lot of those original sentences, things from which everything else seems to stem. And it's just an extraordinary honor to have you here, and I've always enjoyed our conversations, and I just want to give the audience a chance to welcome you here tonight. Thank you. You looked like you had something to say.
Well, I was going to thank you very much for the introduction, and it's a great pleasure. I gather there's some people out there, but as the lights shine, I can see nothing.
I know. It could all just be in our minds.
I can hear
We'll talk
lots of
about
people.
what's in our minds later.
Yep.
So you have been knighted, which is very unusual. I was going to originally introduce you as Sir Roger Penrose, and I know you're a little shy about the title sometimes. But we were discussing earlier how it's inappropriate to say Sir Penrose. It's Sir Roger.
Absolutely, yes, that's right. Yeah.
And I'm just wondering, when Queen Elizabeth knighted you, did she actually use a sword?
I have
an actual
a very poor memory of it, but yes, there was a sword, yes.
Were you and Stephen Hawking knighted at the same time?
No, completely different.
Oh, so interesting. Okay, we'll talk about this. Is there? So one of the things I wanted to begin with is the impact you have had on the general theory of relativity. So here we just have, this is a bit of a cartoon of a black hole forming. And it's a very interesting history because in 1915, Einstein first correctly writes down the theory of relativity, general theory of relativity, which he struggles with for many years. And of course, as you know, he gets a letter in the post in just a few months later, in 1916, from Karl Schwarzschild, who is a German infantry soldier serving on the Russian front. And in the context of Einstein's theory of general relativity, by the way, do you want to have a one-sentence shot at general relativity?
Good. A one-sentence shot.
Well, you have 4 sentences. I don't know. I'll give you as many as you want.
Well, the basic principle is what's called the principle of equivalence. That's Galileo's principle. You drop a big rock and a little rock from the Leaning Tower, or whatever you like, and they fall together. I'm
just going to coax you to do rock star microphone usage.
Yes. I'm not experienced in this, I'm afraid. So let me know when I drift, yes. No, the thing is, so that a little insect sitting on one of the rocks looking at the other, it looks as though there's no gravity.
Yeah.
So you get rid of gravity by falling freely. And now we know astronauts, you see them and the Earth is right there and they seem to be falling freely as though they didn't feel any gravity.
So a lot of people believe that the astronauts in the International Space Station are weightless because they're too far away from the Earth to experience gravity.
Well, that's completely wrong.
Completely wrong.
Yes. Yes, well, that's the basic principle. But you see, it had been known since Galileo's time, but to make it into a theory, that was something different.
So the equivalence principle, just to, because part of my job is I have to translate.
Yes.
So Einstein called it the happiest thought of his life. And he thought, right now I feel heavy in my chair, you feel heavy in your chair, and we think that that's gravity, but there's something wrong with that description because what does the chair have to do with gravity, right? So he imagines if I were up in an elevator and I felt heavy on my feet, what does the elevator have to do with gravity? So imagine cutting the cable and falling freely in this elevator cab, and what you would experience would be exactly what the astronauts experience on the International Space Station. You would experience weightlessness. If I held my phone in front of me and I was following that elevator cab, it would look like it was floating in front of me, just like it is for the astronauts in the space station.
See, I always thought there's a huge irony because science really started through the study of the planets and so on, and then Kepler just found they were really ellipse shapes, and then Newton showed that that came from an inverse square law and the force and all that stuff, and then people used the idea of force for other things, and so science sort of started with gravity. And then suddenly Einstein comes along and says, no, it's not a force. You get rid of it by falling. So it sort of pulls the rug from right under the whole lot.
Right. It's a beautiful idea that what's happened is the Earth has inscribed historically behind its formation, archaeologically in space-time, the curves along which the International Space Station falls freely. So the astronauts in the International Space Station are like falling in an elevator, but they're just doing it smartly so they never crash into the Earth.
That's right, more or less.
They don't experience the unhappy ending to that thought experiment.
Exactly, yeah.
So here it is, 1916, and Einstein gets this letter from his friend who says, it's World War I. The war has treated me kindly. I have had the opportunity to wander through the land of your ideas, and he presents him with the mathematical solution that we now call a black hole. Now, when you were a young physicist starting out, were black holes considered to be a mathematical oddity or real?
Well, you see, they weren't black holes in those days.
They were not
because
black holes,
people didn't. You see, what's called the Schwarzschild Solution. Poor old Schwarzschild didn't live much longer after that. It was a great shame.
He died within the year.
Yeah.
I'm going to encourage you to do this shape with the mic. Okay. Don't worry about it.
I'm supposed to do it that way.
Yeah,
yes.
that's right.
No, that's right.
There we go.
Yes.
Rock and roll,
yes.
Roger.
You see, I'm not really an expert at this kind of thing. Yeah. No, you see, the idea was that, he wrote down this equation which describes the space-time, the curved space-time, which represents a spherically symmetrical body.
Yes.
Now, like an idealized planet, exact sphere. But the thing is that the body itself is way outside this thing called the Schwarzschild Radius. If you could squash it down smaller and smaller and smaller, it gets to the place where, it's the easiest way to think of it is think of escape velocity. You see, from the surface of the Earth, if you imagine there wasn't an atmosphere, you could throw a ball at a certain speed, and there's a critical speed where it will escape from the Earth. Because normally it comes down. You think everything goes up, falls down. It isn't quite true, because if you throw it fast enough, it can escape. So there's a certain velocity. I forget what it is now, but 25.
From the Earth?
Yeah.
To 20 kilometers per second, I think.
Yes, something like that. Anyway, so there is a certain speed which is the escape velocity. Now you imagine the Earth was...
It's like 211. Jesus, sorry. Okay. Anyway.
Yes. Anyway, so the thing is, if you imagine squeezing the Earth down, keeping the same mass, but if it's squashed down smaller, then the escape velocity will be bigger. And the smaller you squeeze it down, even the same mass, there comes a point where the escape velocity is the speed of light. And that's where this horizon occurs. So you have a point that if you had a light signal shining away from the light, from the Earth, if the Earth was squashed down to that size, it wouldn't escape.
Right.
And this is what you call the event horizon.
No.
So a black hole is something much more massive than the Earth, because you couldn't imagine actually squeezing the Earth down like that. But if you have original thoughts were with stars. I think the original thing came with these things called white dwarfs. When Chandrasekhar, he was a very distinguished Indian physicist, and I think he was only 19 or something.
Yes, and he
On
took the
the
boat
boat
from India to Cambridge.
To Cambridge, and he worked out that there was a limit to the size at which white dwarfs, to the mass of a white dwarf.
Mm-hmm.
And if it was bigger than that limit, there was no way of holding it apart. He was using it's a thing called electron degeneracy pressure, but don't worry about that. It's a certain force which
we can talk about
holds
it
it apart. Yes, and that has a limit that if it was squashed down below that limit, then
Well, so here's the dilemma. So Einstein gets this letter in 1916, and he thinks this is beautiful mathematics, but it's not reality. Because of the reasons you're describing, he does not believe that there is a way. I mean, after all, I can't crush this microphone down to a black hole because it resists the crushing, as you're describing.
Yeah.
And so he says, well, it's a beautiful piece of mathematics, but it's not reality. When you started working on black holes, did you think they were just a beautiful piece of mathematics? And they did not have the name yet, black holes, as you said.
No, certainly.
They were just called Schwarzschild Singularity or Schwarzschild Metric.
They were miscalled that, yes.
Yes. So
it's very confusing because there is what's called a singularity in the middle.
Yes.
And that's where the curvatures, we haven't talked about.
So I want to talk about because your work on the singularity theorems was probably your first big breakout, but I just am curious, before you did that work, did you think this mathematical solution was just this platonic ideal in our minds, or did you think it was real?
I think it was pretty real by then.
You did believe it?
Yes. Well, you see, there was the story, in 1939, there was a paper written by Oppenheimer, Oppenheimer of atomic bomb fame, and a student of his called Snyder. And they had this model of a collapsing dust cloud. And that model would describe what we now call a black hole. But the thing about that is people thought, well, it's artificial, because first of all, it's this stuff called dust. Well, dust is just a material which doesn't have any pressure, and so there's nothing to hold it apart. That's the one problem. The other problem was it's exactly spherically symmetrical. Same all the way around.
So it seemed too idealized.
Yes, everything falls towards the center, and so the fact that you get in the middle, this point where the densities become infinite and becomes what you call a singularity, is an artifact. And is this real or not? And I worked for some time with John Wheeler in Princeton.
So 1939, you're a child.
I was.
But it was also, so yes. Oppenheimer, yes.
I was 8 years old.
You were 8 years old.
Yes.
Oppenheimer wrote this paper, as you said, it was published in 1939, on the date, in my understanding, that the Nazis advanced on Poland. So, people weren't paying too much time to the physics journals of that.
I guess not. Yes, that's right.
And so it sort of fell into obscurity, but it was a big paper because the same people who later came to work on the nuclear physics in the bomb came to understand the nuclear physics in stars, came to understand that the pressure from the nuclear physics was not sufficient to resist catastrophic gravitational collapse to a black hole.
Well, you see, the story sort of came back again because of quasars. Originally they were radio objects, and then people had visual, and these were very, very bright objects. And they were so bright, they were brighter than an entire galaxy. And people were very puzzled by this, and they didn't know whether they really were that bright, were they much closer, and the redshift, which told you how far away, maybe there was some other reason for that. And there was a lot of argument about it. And it was very puzzling because not only were they producing this much energy, but they also varied very rapidly within a period of a
Which
week
suggests
or so.
that they're spatially small.
That means that there has to be small, that's right.
Spatially small, but not necessarily light. They could be heavy.
Heavy but small. So people were they were very puzzled about these things. It wasn't completely clear what they were at that time, but people realized that you had to have something which was down to the sort of sky. You see, the Schwarzschild Radius, which is this thing we talked about, for the sun is what a meter.
It's 3 kilometers, but 6 kilometers in diameter. If the sun were to be a black hole, it would be 6 kilometers across. So imagine taking the sun and crushing it into Central Park, basically.
Yes, but sure. But you see, the bigger...
No big deal.
The more massive it is, the less the density. See, the point is that the sun, if you squashed it down to that scale, it would be pretty dense. And okay, you could, if it were, there are stars which are that sort of density. But if you get bigger, then the density goes less. I mean, it's the way things scale. So the things, if they were like a whole galaxy squashed down to that size, the density wouldn't be big at all. It would be less than air. So it's the way that scales things. If it's big enough, then this horizon, as we call it, the Schwarzschild Radius, is not so puzzling.
So I want to ask you this. You're saying that these quasars, so I just want to emphasize that this went on for decades, that people did not believe that these objects were real. They thought they were just mathematical. And so when you were talking about quasars, what year are we talking about? This is before your work.
This was around about 1962 or something like that. So right
before, like really on the cusp of when you did some very fundamental stuff.
Well, you see the confusion. You see, Wheeler was very interested. Is the singularity that you got in the Oppenheimer-Snyder collapse an artifact of the symmetry and the fact you got dust, or is it a general phenomenon? And that was the question he raised. And at that time, there was a paper written by two Russians, Lifshitz and Klatnikov.
Yes, and Belinsky, Klatnikov, and Lifshitz also.
Yes, but wait a minute.
Belinsky came later.
Lifshitz and Klatnikov seem to have proved that in general you did not get singularities, so that it was an artifact. And I had a look at this paper, and I didn't see quite how you could prove anything like this by those methods.
So tell us what a singularity is first. So
well, think of it.
Schwarzschild has a solution. Light cannot escape. It means these objects are dark, because if light can't escape, they're by definition dark.
You see, that
they haven't earned the name black holes yet.
Yeah, that used to be what was called a singularity, but we don't call that a singularity now,
So
because you could be there. I mean, it might be unpleasant, but you wouldn't be.
That's so British. Can we just acknowledge our brother? It might be unpleasant to cross
it depends
the
how
event
big it
horizon
is.
of a black hole.
It depends how big it is. Let's not go into that. But you see, the singularity, you imagine something where the density, say, goes to infinity. I mean, the density of that glass is whatever it is.
It's not
It's not infinite.
It's not infinity.
And you can have things much denser than that. And then you have these white dwarfs, which are extremely dense, or the neutron stars, which are the density of a nucleus, which is enormous. But we're talking about densities which are infinite. And that's this model that Oppenheimer and Snyder put forward. The density went infinite in the middle. And your physics goes crazy. So how do you describe a thing when the density is infinite?
So I actually have this figure from your 1964 paper, which is one of the most beautiful scientific papers ever written. It's 2 pages long, Roger. Do you know what it would take? You know the Mark Twain quote, I wanted to write you a short letter, but I didn't have time, so I wrote you a long letter instead. It is a 2-page letter. And it has this beautiful diagram in it, which we'll talk about.
I should explain that time is going up the picture.
Time is up, and there's 2 spatial dimensions.
Yes.
But we can't draw the third, because none of us have that
capacity. You have to throw away a dimension and draw the picture. Yes, right. Yes. Sorry, I should be doing this.
We're not going to go into detail into this picture, but it is so iconic. This was drawn by you in 1964. Showing what you're describing, which is the idea that when a star collapses, it first forms an event horizon, which is the region where the escape velocity, as you put it, would be greater than the speed of light.
That's the cylinder that you see.
That's the cylinder that you see. And then after that, it just keeps falling. And this is something people don't understand. So many people have said to me, isn't a black hole this really dense crush of matter? When I get to the event horizon, shouldn't I be like banging on some really dense crush of matter? And this diagram is so iconic in that it shows that the matter itself cannot help but to keep falling. It cannot stay there at the event horizon any more than it can travel at the speed of light.
Yeah, but the point about it, of course, was that in this picture, it's a spherically symmetrical picture, like the Oppenheimer-Snyder picture. Right. And what I had to show was that you still get a singularity even if it's irregular.
So the singularity is what forms when the star keeps collapsing catastrophically, even inside what we now call the black hole. And then what's the singularity exactly? What is it?
Well, we don't know what it is. It's where the physics goes wrong. All it tells you is that the physics goes wrong. The current theory can't explain what happens. You get infinite densities or something, infinite curvatures, and something like that goes wrong.
So you are credited with proving that no matter what, in the general theory of relativity, you will create a singularity. It's not about the special circumstances.
Yeah.
It's not, whether it's symmetric. It's not whether it's dust. It is an absolutely generic and unavoidable prediction of general relativity that you form a singularity. And so a lot of people have misinterpreted that as saying singularities are inevitable. But I've always said what you did was you proved what we've never been able to measure, which is that relativity fails at some point.
Yeah. Well, you see, you have to have a condition which says there's a point of no return. And this was the problem. And there's a sort of strange story about this, because I developed certain techniques of how you might prove things like this, using topological ideas and so on. But I didn't have a criterion which tells you the collapse has reached a point of no return. And I was puzzling over this. And a friend of mine, Ivor Robinson, who was an Englishman who had a job in Dallas, Texas, but he was visiting me. Oh my God! Yes. Oh, you're
There's
God?
some stories there.
Anyway, so the Americans all loved him because he had such a way of speaking. He really did. He had a wonderful way of using words. And he was using these words on me. We were walking along the street, you see, and he was describing things. And it was wonderful. And I liked to listen to him too. And then we came to a road, and we crossed the road. And as we had to watch out for the traffic, he stopped talking.
I remember this story.
And then we got to the other side, and he talked again, you see. And then when he left, I had this strange feeling of elation. And I couldn't think, why am I feeling happy? See, I don't know. Well, okay, it was an interesting conversation, but that's not it. So I went through the day, and I said, well, was it what I had for breakfast? No, I don't think that was it. So I went all the way through the day, and then I reconstructed the crossing of the road. And then I remembered that I had an idea crossing the road, which was this idea, you've just rubbed it off now, this idea of a trapped surface.
Yes. We'll get there. I'm a step behind. Yes, the trapped surface.
It's actually in the picture. Don't worry about it. There's a trapped surface in the picture.
Right.
And the idea is that this surface is something, it's the little ring in the middle of the picture.
Yeah.
You have to throw away a dimension. It looks like a ring. It's really a surface, like a sphere. And the point about it is, if you imagine that a flash of light occurs all over that surface, you see, usually if you imagine a curved surface, then if there's a flash of light on that surface, then it's convex one way and concave the other way. And the concave part, the flash gets smaller, and the convex part, it gets bigger. The thing about a trapped surface is it gets smaller both ways. And that was the criterion. And I realized that if you go inside this region, which is what we call the horizon, it doesn't have to be symmetrical at all. But if you get this criterion where the surface is trapped in the sense that the flash of light goes in both ways, then you're in trouble. And that was the condition.
And by in trouble, you mean you formed a singularity.
Yeah. So the theorem was to show if you have a trapped surface, and it can be quite completely irregular, then you have a singularity.
Now, this is an absolutely stunning mathematical theorem. It really is, because of the generality. It's exactly what you're describing. It's not the specifics. A specific star with these specific conditions can make a singularity. It was an absolutely general swatch. It said any collapsing object will form a singularity. It's a huge result. Did you immediately get a response? I mean, general relativity at this is 1964.
That was 64. It was 1964 when I proved the theorem, yes.
And
right.
By then, relativity is already 45 years old, and nobody has really taken it seriously. Black holes are not believed to be real. Nobody's actually seen a black hole. Did people ignore it? Was there excitement?
Well, it took a while for them to get the hang of it. It was using the sort of techniques people used was either to look at exact solutions like Schwarzschild's one, or they used computers.
Which were not very good back then.
They weren't that good at that time, and you really couldn't tell, you see. And even now, you wouldn't be able to tell if it's genuinely a singularity, because you have to go beyond what the computer can do. So this was using techniques which were not used in this area.
So can we just discuss for a second again, so people understand the impact? Why is a singularity so bad?
Well, because the physics gives up. And because it's bad because... I should sort of qualify that a little bit, because general relativity is a classical theory. It doesn't use quantum mechanics and so on. But if you follow the physics, you've got equations which tell you what happens, you know what happens now, and these equations tell you what happens a little bit later.
Yeah, we like predictability. We like to be able to say what the consequence is.
Yeah, but as long as... The trouble with the singularity is you get to a point where the equations go wrong. They say, oh, you get to infinity. And once you've got infinity, there's no way of proceeding.
It was almost like matter was blotted out of existence.
Yes.
So if you were the stuff of the star in your drawing that fell into the singularity, it was like it fell out of the universe.
Well, that's more or less what happens.
It ceased to be.
Yes.
Okay, so that sounds really bad for physicists.
Yeah. Sure.
So we don't like that? We don't like that idea?
A lot of people don't like it now, yes.
So do you like it now? Do you think singularities are real?
Yes, well, you see, there was a bit of a discussion between Stephen Hawking and me. You see, I proved this thing. Don't believe what you saw in the film, because in that film, there was somebody...
I don't know which one you mean, because there have been several.
The one, the theory of everything.
Okay.
And in that film, there was somebody who was supposed to be me.
I know. There was an actor who played you. I saw that.
It didn't look like me.
It didn't look like you.
And the lecture didn't resemble any of the lecture of mine. And in that audience was Stephen Hawking with sparks coming out of his head or something. But he was being inspired by the lecture.
Crackling with electricity.
Yes. Now you see, okay, well, I did give a lecture in London about that, it's true. But Stephen Hawking wasn't there.
Well, let's make our smooth transition to the Stephen Hawking slide. Stephen Hawking and you share celebrity over the singularity theorems because he thought about it in the context not of black holes, but in the context of cosmology.
Yeah, well, let me slightly... The film was completely wrong on that point.
We're back on the film.
Not so utterly wrong, because Dennis Sharma, who was a great friend of mine, and I learned a lot from him about physics, and he was a great man. But he was at Cambridge. This is a lecture in London, and he invited me to give a repeat of this lecture in Cambridge, which I did. And Stephen Hawking was present at that lecture. But the main thing was that he talked to me afterwards. He and George Ellis had been working on the singularity in a much more specific case. It wasn't as general as this at all. So they'd been working on a different method of looking at these things. And then I described the techniques I was using. And Stephen picked up on those very quickly and was able to use the same mathematical result as I had, but applied not in a sort of reasonably local way, but going out to large distances and talking about cosmology. So he used the result in a kind of reverse time way to apply it to cosmology, which was a very ingenious thing to do. But then later on, he generalized the arguments and spent a lot of time doing more, using more general arguments than I'd used to prove that you get singularities in the Big Bang. He says you can imagine go back in time now, and you're thinking about the universe. The universe was expanding, so back in time it's collapsing. And does the same sort of result apply there? And you still get singularities in cosmology. And this is what he was doing then. And then later on we got together and proved a theorem which sort of encompassed pretty well the things we'd done before.
The Hawking, the Penrose-Hawking singularity theorems are huge in the history of general relativity, and they were incredibly important in terms of challenging everyone to understand that even relativity, as sacred as even now, all these years later, has been confirmed by every observation, every test.
Very much stronger now.
Every
Absolutely.
position.
Yes.
We believe relativity is absolutely correct in the range in which it's valid. But you and Hawking back in the 60s and on proved that it's never going to be valid forever. basically. So
Yeah.
I often say you didn't prove that singularities exist in physics, you proved that relativity fails at some point.
Yes, well, the usual argument was you've got to bring in quantum mechanics, you see.
So
It
here we
says that-
are.
yeah, I mean, in my paper, I never said, actually, that this theorem proves it's singularity. I just said, maybe this is wrong, that. There was a list.
Right.
And one of them is that the physics becomes all quantum mechanical.
it's
The
still-
space-time becomes quantum mechanical or something.
It's still a few years before even the term black hole is coined.
Oh, yeah.
So John Wheeler coins the term black hole in 1967.
So I'm told. I never was quite sure that we weren't using that term before, but I don't know.
I don't know.
Yes,
Well,
I
you
know
would
that's
know.
the story. No, I don't actually.
So what did you think of the term when it,
I
it's
think it was
50
pretty
years
appropriate,
after
actually.
relativity?
Yes, I think it was a good
You
term.
were delighted.
Yes.
Weren't you tired of saying complete gravitational collapse before?
I don't
Just a
think I
black
used that
hole?
term.
So I want to talk about the Penrose diagrams, which you do next. And I just want to say, people don't necessarily always appreciate that there's different branches of mathematics. And there's different talents and abilities that go into different branches of mathematics. There's so many, it's like languages. It's like a proliferation of branches. You are a particularly extraordinary spatial thinker, visualizer. You're incredibly creative in that space. It's just, it's really probably, I would say, unparalleled.
Well, there are others too.
Our time.
I think it's the biggest division. You see, when I was in school,
Yeah.
School, not university, and I seemed to be able to do mathematics pretty well, and most of my friends then weren't so good.
You weren't bad.
But so I thought,
Wasn't bad.
well, when I went to university, I'd find people who thought like me. You see, what I didn't expect is I found more different ways of thinking about things in mathematics than I'd ever experienced before, and it was quite strange. Two people would talk to each other. I find this often, and I didn't understand what the other person was saying, and he didn't understand what I was saying, but somehow we could realize we were groping for the same thing. Mm-hmm. And how one got this understanding without really in detail understanding the thought processes was a very mystery to me. But I think the main division, and I certainly noticed this in thinking, was whether you thought geometrically or in terms of equations and things like that. And I was very much on the geometrical side. There was only one other in the class, I think, who was also very geometrical.
Now, was that derided? Was that considered
I think there's
peripheral?
a selection effect. This is my theory. You see, I think the trouble is it's very hard to examine. You see, when I did my final exams...
You see it or you don't see it, sometimes
well, you see,
with geometry.
let me explain. See, I had... At University College London, where I did my undergraduate work, we did the general papers in the first 2 years, and then your special papers, what you specialized in was the last two papers at the end of 3 years. And I specialized in geometrical things. It was some pure geometry and algebraic geometry. And I thought, yeah, these will be things I can do, you see, easily. The trouble was, I could see how to do the problem, but how do you write down the solution? You have to translate it out into words. So there are a lot of words, and the translation from how to do the problem into the words, and I was always slow at the writing, and I didn't do it. It turned out those were not my best papers. My best paper was in algebra. And see, what I'm trying to say is that I think that there's a selective disadvantage in being geometrical thinking in mathematics, that people don't do so well in the exams if that's the way they think.
Oh my gosh, when I was, just between you and I,
When
I was coming out of graduate school, people were saying your visualizations, like your leaning on visualizations is your weakness. And I remember thinking, well, I thought that was my strength.
I see, yes.
And so this is an example of one of the things you taught all of us, which is what we now universally know as Penrose diagrams. There are Penrose diagrams for any possible number of spacetimes. But just like there's a map of the Earth, you take a sphere, which is the Earth, but you project it onto a flat sheet of paper, and you know that you're doing a projection. You're making some map and some set of rules for how to do that. The Penrose diagram is a map and a set of rules for taking an infinite space into a finite region.
Yeah, it does that.
It does do that. And so this is we don't need to go into the structure of it, but this is Minkowski space, which is basically flat space-time.
Yes.
But infinite flat space and time mapped onto a beautiful little diamond.
It's special relativity.
It is special relativity.
Yeah. That's Minkowski.
And why did you do this? What motivated you to do it? Because it turns out to be incredibly powerful. I was teaching general relativity, this also just between you and I, this semester, and the idea of using Penrose diagrams is such a wonderful way of teaching students how to visualize something in its entirety in like one scoop of the eye.
Well, I'll tell you, I was in Syracuse, where this was in 1961, would that be? I was in Syracuse, New York State, and there were quite a lot of relativity people gathered together. Peter Bergman, who was Einstein's last student, and he had collected this group of people together there. And one of those was Andrzej Trautmann, who was a very distinguished Polish relativist. And he was giving a lecture on gravitational radiation and what the field looked like when it was far away. Very good talk, but it was absolutely full of equations, and I was not very good at following all those equations, and I thought, well, there must be another way of doing this which saves one writing down all those equations. Now, you see, I was familiar with the idea of conformal geometry. You have that Escher picture here?
I do.
Yeah.
Okay, I'm going to skip ahead. Let's get to this because this is a great example. We're going to come to all these things. It's here. Wait.
You got a moving picture.
I've got it.
The next one, is it?
I've got a low battery, apparently. There
we are. That's right. Yes. Now, that's a wonderful illustration. Mm-hmm. Now, it's a conformal picture. You see, it's a picture of an infinite universe. The universe is two-dimensional, and it's inhabited entirely by angels and devils, and they interlock.
I inverted this, by the way. Usually the devils are in black and the angels are in white. I don't know.
My God, you've got it the other way around. You're right, yes.
Little Dr. I don't know if there's some going on. Yes, I inverted it.
You are right. That's the devils are supposed to be black, and the angels. Well, never mind about that.
In the original Escher, it's the opposite.
They were, yes, but I don't think there was any racial
No, I was thinking more good and evil. Like, I don't know, bats are cool. I'm like, bats are cool. So I'm going to highlight the bats.
Okay, well, I think I'm with you actually on that one. The bats, I like bats, I agree with you. But anyway, in this picture, you see, it's what's called a conformal representation of this geometry. And you have to imagine that all the angels are really the same wherever they are, no matter how close to the edge they are. Mm-hmm. They think they're just the same as the ones in the middle.
Right, so it falsely looks like the figures on the periphery are smaller.
That's right.
Actually, that's just like a Mercator projection of the Earth. You're not reading distances properly.
Yes.
They're as big as the ones in the middle.
That's right. But you have to think in this projection, or whatever you call it, the angles, if you look at the angles on the devil's wings or something, and you see they're always the same, or if you look at the shape of the eye of the devil.
It's unaffected by the map that brings it into the finite region.
It's just smaller, and small shapes are exactly the similar shapes. They could be smaller, but they're the same shape.
You have to learn how to read a map.
Yeah.
You can't take a map at face value, basically.
But anyway, it's a useful mathematical way of describing a geometry is this conformal representation. It's a kind of geometry called hyperbolic geometry. Don't worry about that. But in this picture, infinity is represented as a finite boundary.
Right, so that's infinity. That's infinitely far away.
Infinity is that finite circle around the edge.
When did you first see this image? This is Escher. When was this? I don't know when this was drawn, but when did you first discover Escher? Because I just want to throw out a quote that you said, which is when you first saw an exhibition of his, you said, "I had no idea what role I would play in his life or he in mine."
I don't remember saying that, but I could have said that.
I'm telling you, Roger, it was recorded by the BBC 4.
I see. Well, anyway, yes, I went to it was, 1952 or 4? I don't know. It was in my second year.
It was 1954 in Amsterdam.
That's it, okay. It's in my second year as a graduate student. And I...
so you just stumble on this show?
Well, it was one of my lecturers. Like, he was just getting off a bus or a tram or something, and I saw he had this catalogue then. What on earth's that? And it was one of Escher picture, Night and Day, with the birds white and black and all that stuff. Yeah. And I said, what on earth is that? And he said, oh, there's an exhibition going on. You'd probably be interested in it. And this was in the Van Gogh Museum, and this was Escher. I'd never heard of Escher before. This picture was not there. There's an interesting story there too, because the geometer Coxeter had also been at this Escher exhibition. He was at the same International Congress of Mathematicians, which was in Amsterdam at that time. And he had suggested to Escher to represent this kind of representation of hyperbolic geometry. And Escher learnt it beautifully and extremely accurately. It's amazing. He claimed he was no good at maths, which is completely false, clearly. But maybe he wasn't so good at arithmetic or something. But
well, maybe he didn't understand maths could also be visual, because one of the points I wanted to make that we skipped past because we got carried away was that the drawings that you make are mathematically formal objects.
Yes.
They're formal mathematical objects that can be calculated with.
But they're very geometrical and visual.
Geometric and visual, but not just cartoons. You can calculate with them.
That's right.
You can sum them, you can, add them, and then you can read at the end of the day a quantitative result off of the drawing. And so that is an ingenuity that I just think only you and Feynman really had, which was that you can calculate with drawings.
Well, he had obviously made a great, the Feynman diagrams.
The Feynman diagrams are ingenious.
Yeah. But no, there are a lot of other people who thought that way, in a geometrical way. I'm not talking about, no. I don't think it's a majority, but
that's a breakthrough. It really is. But anyway, so you were saying Escher doesn't see himself as mathematical because maybe he doesn't understand, he doesn't acknowledge the math.
Oh, he clearly understood geometry very well.
But he didn't know you. You just stumble on his exhibition.
Yeah.
And then you are motivated by that to think about some things.
Yes, I don't know whether you got that. I'm getting you out of order with your pictures.
I have this. Oh God, I love this.
I'm sorry. Yeah.
This is a paper you wrote after you saw Escher's exhibition with your father. L.S. Penrose and R. Penrose are the authors of this paper.
That's right.
And you reference, and you did not know Escher at the time of writing this article.
No, I'd been to the Escher. I don't know, you got that picture of what he called relativity with the staircases and going around.
Yes, we'll come to that.
Yes, that's right. Well, you see, I'd seen that one in the exhibition. It was a big room.
Right here.
Yeah, it was a big room with all these Escher. Yes, that's the one, yes. Mm-hmm. And I remember being particularly struck by this one. But there were all sorts of them, which I found completely amazing. Mm-hmm. And so I went away and I thought, I'd like to try and do something, not at that sort of level, but I'd like to do something impossible that I hadn't seen in the exhibition.
Who doesn't want to do something impossible?
Yeah, I'd like to do something impossible, yes.
So you decided to make an impossible figure.
An impossible picture. Well, you see, I started drawing things with rivers and bridges and roads going in impossible ways, you see. And then I whittled it down to this, what I thought was kind of the most...
This is the impossible, your famous impossible triangle. It's quite
yes,
famous.
Well, it's,
You drew this one, actually. This is your drawing.
That is, yes. Yeah. I did draw that one, yes. And I drew this picture, and, well, I don't know if it's that exact one, but I drew one of those pictures. And I showed my father, and then he started drawing impossible buildings. Impossible College, I remember he drew a picture. And then it sort of developed this into the staircase. Mm-hmm. And we hadn't seen anything quite like that exactly in Escher. In the meantime, Escher had produced the one he calls Belvedere.
Skip ahead, yeah.
Yes,
I just want to skip past this to the one that your father did. Hold on, let's see. So this is from your paper with your father.
Yes, that's
your impossible triangle and your father's impossible staircase.
Yes, that's right.
Yeah, and then Escher does this waterfall drawing based on the impossible staircase.
We sent a copy of the paper. You see, we'd written this paper and we couldn't think what the subject was. You said, what on earth is the subject? And then my father said, well, I happen to know the editor of the British Journal of Psychology, so let's say it's psychology. So he was pretty sure he could get it accepted. So we sent it to the British Journal of Psychology. And indeed, it was
You
accepted.
were aiming low, you're right.
Yes. And so that's where it was published. And then we sent a copy to Escher. And it was some friend of my father's, I think, who forwarded it to Escher. I don't know how it got to him. But anyway, so he then developed these two prints, the waterfall, which I think...
But he sends them to you directly, personally, doesn't he?
He
sends you the original drawings.
Oh, yeah. Well, I had my father got an original print of the staircase, which has a dedication in the corner.
Oh, it's lovely.
So
and it's at that Ashmolean now? Is that where it's
it is now in the Ashmolean, yes. Mm-hmm. Well, I actually have, I don't know how I got so many. I've actually got 9 Eschers.
I don't know how.
I've
got 2 Dustin Yellens. That's how this works.
Well, Escher directly gave me one when I visited him, you see. Mm-hmm. I had his phone number because my father communicated with him. And I just out of the blue phoned him up and he said, just come around and have a cup of tea. And
so I also understand that somebody gave, and I just happened to have found this just accidentally, that somebody, can we turn the volume off of this? Sorry, volume off. Sorry. This was Picasso being handed a picture of one of your impossible drawings.
I see.
And that's quite amazing. And he said something, he was so wowed about what you were doing in geometry. And do you remember that, hearing about that?
No, I don't know what he said.
I don't remember what he said either. I think he said something like, you should have been a cubist. And by the way, I disagree. He should have been a physicist. Okay, sorry, I'm keeping you in physics. But I think he said something like, you and your father should have been cubists.
Yes, well, that's very flattering. Yes. No, I didn't actually know he'd seen any of these things. Yes, that's interesting.
Yeah, it's quite amazing. So that's allegedly, if we have the history right, Picasso looking at your impossible triangle.
Well, I can't tell because I can't see the picture.
And then, yes. And then this is also, just to quickly talk about drawing, one of your notebooks, which I love, which is just full of drawings and math. And so I just wanted to ask you about your notions of creativity in math and physics. You know, when I first started studying those subjects, I thought they were uncreative fields. Thank you for laughing.
Yeah, well, all right.
And
yes.
and I thought, you know, it was just, you just followed rules. Then we're going to talk about algorithms in mind in a second.
Yes.
And I don't know exactly when the transition happened, when I realized this was an outrageously creative field. And this idea of, you know, drawing in your notebook, it's not that you're trying to make something pretty, you're trying to solve a problem. And you're trying to use incredibly creative solutions. Anything you have, it's almost scrappy, like anything you have at your disposal to solve these incredibly hard problems. And I was so influenced by your work because it was so original, the approach, the ingenuity of thinking, oh, I could draw this diagram and then I can see it immediately when the calculation would take me 15 pages. If I simply draw one of these diagrams, I can see right away where the trapped surfaces are, where the event horizon is, where the singularity is. And it was really powerful. And I'm wondering if you had a similar experience of realizing, oh, this is a creative field.
Goodness. Well, I mean, I can slightly digress from that because you see, it's very hard to say when am I being creative or not. I mean, often you find something which somebody found years and years earlier, and you don't even know that. Mm-hmm. But you're still being creative, I suppose.
Right, yeah.
So
I just mean, you know, searching for tools to find solutions the way we do with language. Like we think language is creative when we make original sentences. Why don't we think physics is creative? Or math is creative when we make original sentences?
I think it's awfully difficult to know about creativeness and so on. You see, my take on this is a little bit different. When I was an undergraduate, I had a good friend, Ian Percival, who we used to talk a lot about mathematics and things, and we talked about mathematical logic. We didn't know much about it, but we talked a lot about it. And I'd heard vaguely about Gödel's theorem, which seemed to say, as I understood it, that there were things in mathematics that you couldn't prove, but you're true and you couldn't prove, and I didn't like that idea. And so when I went to Cambridge as a graduate student, I went to 3 courses which were nothing to do with what I was supposed to be doing. Maybe that's to be creative, going to courses which nothing to do with what you're supposed to be doing. So I went to 3 courses. So I was doing algebraic geometry. And I went to a course by Herman Bondi on general relativity.
Oh, not bad.
So that was
That's pretty good.
amazing course of lectures. I went to a course by Paul Dirac on quantum mechanics.
Not bad.
Now what
not
can
bad
you do
education.
there? Yes,
Not
absolutely.
bad.
And I went to a course by a man called Steen on mathematical logic. And I learned about Turing machines, and I learned, how basic idea of computation and that sort of thing. Mm-hmm. And I learned about Gödel's theorem. And I learned it wasn't what I was afraid of, that there were things in mathematics that you couldn't see that were true and you couldn't see, because it wasn't like that. Mm-hmm. It was like, if you've got some restricted way of proving results that you could put on a computer. So you've got a system of rules that you could put on a computer, and you can put the theorem on the computer and say, ask the computer, can you prove that, say? And it has a long string of things, and maybe it would say yes. And if it says yes, and then you have to believe it's true. Now, why do you believe it's true? Because you've looked at those rules, and you say, yep, that one's okay. Oh, I see that one too. And you've gone all the way through, and you say, okay, all those rules, if you follow all those rules, and it says, yes, it's true, then it is true. Okay, what does Gödel do? He produces a statement which you can see, the way it's constructed, that it is true if you believe that those rules only give you truths. Yet, it cannot be proved using those rules. Now, that was absolutely stunning to me.
It was absolutely stunning.
Absolutely stunning.
And in my role as translator, may I just interject for a second before you continue? Because I know nobody else, except for Jim Simons, knows what we're talking about right now. So Gödel proved that there were facts among the numbers that could never be proven to be true in the context of a particular axiomatic set of mathematics. So, for instance, 1 + 1 = 2 can be proven to be true, but he proved that there were statements like, this statement is unprovable, which could not be proved to be true, which therefore made it true.
It's because the meaning of it you understand.
That's right, because you have to step outside
Yeah.
of mathematics to recognize that it's correct, true, but it was not a theorem. It did not lie among the infinite list of possible theorems.
Yeah, it's amazing.
I mean, I'm a super huge Gödel theorem fan. I've spent a lot of time obsessing about this, and it is chilling, because it was chilling because Hilbert, who was the greatest mathematician of that era, didn't demand, but he made a call out to all of the mathematicians to prove that all correct facts amongst the numbers could be proven to be true. I mean, who wouldn't believe that that was the case? Hilbert was being completely sensible. All facts among numbers that are true could be proven to be true. And here comes Gödel, and he says no. In fact, there's an infinite. He says, in fact, there's an infinite list of facts.
But the key thing
about
is
the numbers that can't be proven.
What you mean by proof, you see.
Yeah.
Because if you fix a certain set of rules, and that is what you mean by proof, then you're too limited. And what he's showing, that there are always other methods. No matter how...
But it's always one step up. It can't be self-contained. It's always one step outside of whatever system it tries to be in.
But you still see, by the way it's constructed, that it's just as true as anything you prove using the rules.
So but he goes further, and Turing goes further to say that most numbers are numbers about which we know nothing.
Well, I don't know.
That's true. The biggest infinity of numbers are numbers about which we will never prove the facts about those numbers. So there's levels of infinity, and the biggest infinity are the uncomputable numbers.
Well, you get a lot bigger than that.
So this is a segue into what I want to ask you about as a segue into...
You were asking about creativity and all that.
Yes.
See, what I was going to say is that what I'm trying to say is that you can always break out of the system. And I mean, you can say that's being creative because, Gödel was certainly being creative in using this type of argument, which nobody perceived of before.
It was wildly ingenious.
Oh, absolutely. Sure. But I guess my argument was a little bit different. It has to do with whether I guess maybe you're coming to this, whether our brains work as computers. That was the question.
Yes, so I think this is the beautiful segue into you were
yes.
You were interested in Gödel's, so let me just paraphrase it so I can prep for where we're going to go with your other theories, which is that you were interested in the fact that there are certain things that can't be computed in an ordinary way. And that there are numbers, for instance, that relationships amongst numbers, facts among numbers, and numbers themselves that cannot come out of conventional mathematical algorithmic thinking.
Well, you just make the convention bigger, you see.
Right, but even then the convention gets infinitely big. So you were thinking about Turing, and Alan Turing, of course, is the great genius who gave us the idea of a mathematical computer, a digital computer, a mechanical computer, electronic computer, and an instrument that computed things by following rules. And Gödel's theorem suggested, well, if you follow those rules, you're still going to miss a larger infinity of facts.
Well, Turing was well aware of the Gödel result, and he generalized it.
Yeah. So what does this have to do with consciousness in the mind, which is where a lot of people are like, Roger.
Well, I mean, can tell you. You see,
what are you talking about?
No, I mean, the idea more or less came when I was a graduate student, and it was these 3 courses. And I heard the Steen's course, and it told me, you see, it's not quite creativity, because you can take Gödel's creativity, and it's the understanding that it gives you. That was more the point.
Right.
So I was trying to say, understanding, what Gödel was telling me, that mathematical understanding is not a computable process. It's not a computation. Because there is all the arguments gets a bit more complicated than that, but the basic thing is that you can always, once you see how to do the computation, you can see how to go beyond it. Let's not go into the details of that, but that's the basic argument. And so I came to the view, I was certainly a physicalist and thinking that what's going on inside our heads is the same.
I know you have no patience for that sort of new agey, which is what I think you get thrown sometimes.
I get thrown in,
Right.
Let me explain, that I certainly believe it's physics going on inside our heads. And it's the same physics that's going on in that glass. It's just organized differently. And different things about that physics are being made use of in different ways. But you see, I'd been to this course by Bondi, and I thought about general relativity, and I knew about Newtonian mechanics. Can you put that on a computer? Well, people do. Okay, you have a little problem about continuous numbers as opposed to approximations. That's not a trivial problem. But I thought that was not the issue. Okay, you can put it on a computer. You can put Newtonian mechanics on. You can put general relativity on a computer. And people know with LIGO, they see these signals and they know, well, that's because of computations that people know what black holes do when they spiral into each other and they produce signals like that. Sure, you can put that on a computer. What about quantum mechanics? Well, you see, I went to Dirac's lecture. Well, what about quantum mechanics? Well, the first lecture that Dirac gave, he was talking about the principle of superposition. So we say you can have a particle here, and it could be here or it could be here. You have states of the world where it's here and here at the same time, in 2 places at once. And he sort of illustrated this. He said, well, why not this piece of chalk? He had this piece of chalk. And I think he broke it in 2 and imagined it was here and here at the same time. And my mind wandered at that point. I didn't quite hear what he was saying. And he went on to the next topic. And I sort of remembered him saying something about energy, but I didn't quite see what that had to do with it. So I worried about that ever since. So I thought, okay, well, here in quantum mechanics, you've got this problem, which really is a problem, which is what we call the collapse of the wave function. The wave function says you can have the thing here and here at once, but you don't see it here and here at once. You see it either here or here. And that's because, well, it's Schrodinger's cat. You see, he gave this example of a cat which could be dead and alive at the same time. And he was really using this as an illustration of his own equation. He's saying if you follow my equation, well, that's his equation, then you could have a cat that's dead and alive at the same time. Well, that's absurd. That's more or less his argument. Well, many physicists say, oh no, Schrödinger says you could have a cat that's dead and alive at the same time. Schrödinger was really trying to say there's something wrong.
Right, and I mean, Einstein is famous for having to try to say something's wrong in quantum mechanics, and then it turns out to be true.
Well, you see, often these things are true, but this doesn't mean this particular thing is wrong.
So I just want to take a step back and say that there's a strong AI attitude which you're reacting to. So can we just establish the strong AI attitude which you are objecting to, which is that computers which are algorithmic are going to create conscious minds?
Yes.
Would that be fair to say?
Yes. I mean, that's fair.
That's the fair representation of that position.
That particular viewpoint,
right. But you are saying because Gödel proved that algorithms cannot reveal all truths and that human beings are able to step outside of those algorithms and say, well, that's a true fact among the numbers that's not algorithmically provable. Does that mean that human beings are doing something that algorithms can't? Would that be fair? Yeah,
well, it's sort of I mean, you have to be a little bit more careful about the argument. But basically, it is. Some people say, well, you know, we got such complicated algorithms in our head that you can't know what the algorithm is, so how can you use Gödel, you see?
I guess.
But that doesn't work.
What doesn't work?
That argument. Because how did this complicated algorithm come about? And it's natural selection, sure, I agree with that. But then natural selection did not select against, I mean, you need a complicated algorithm that can do Gödel's theorem is not selected
Right, so this is what I was going to challenge you on.
Yes.
It's like, okay, clearly Gödel's theorem says that this particular algorithm can't yield things, but clearly what Gödel did is algorithmic. No. You could say code theorems, and then, you know, it's just maybe it's like your tilings, which we're looking at here, which we did not get to discuss.
No, but it's
Roger's ingenious Penrose tilings. But they take more than one algorithm. They take more than one shape. It's not possible to do them with only one algorithm or only one shape.
The point is whether you understand what the algorithm means. I mean, you can put an algorithm, you can take any old theorem, you see, which is true, and you can make an algorithm that says this particular theorem is true. But why do you believe it? You've got to understand why that algorithm gives you truths.
You're after something with consciousness. What are you after? You're after qualia.
You're after
the experience. You're after the experience of consciousness.
Sure. Consciousness is many things. It's appreciation of the color blue, it's love, it's kindness, it's pain. It's all sorts of things. I only concentrate on one little thing. Sometimes people say, why don't you talk about it? Well, because I don't have anything to say about them. But this one little thing is the understanding, which I'm claiming. The quality of understanding is not computational. That was my argument. And I go to Gödel for that.
Okay.
And it's okay.
And I think that's indisputable. I think that's absolutely...
Well, lots of people dispute it.
Well, they're not invited to the after party.
Okay, well, that may well be, yes.
No, but I don't understand the connection with quantum mechanics.
Yeah, but
so
that's...
how can you take me to why I need to go to quantum mechanics?
Okay. Well, you say
he's shushing me. Or he's quieting me, or he's soothing me. It's one of those things.
I'm sorry, I'm interrupting you.
No. You were soothing my anxiety about quantum mechanics.
Yes. No, I'm trying to say, I mean, these three lectures, which have nothing to do with what I was doing, you see. Maybe it's an advertisement to go to courses which have nothing to do with what you're trying to do.
It's
good for that, yes.
That's what we're all about here. That's what we're doing
that's
here.
True. But you see, particularly the Dirac lecture, was this question about why you don't see piece of chalk in two places at once. And since I didn't hear his argument, which would have calmed me down probably, you see, I worried about that ever since. So I worried about this thing called the collapse of the wave function. It's something, see, people talk about quantum mechanics and say it's the most wonderful theorem, most wonderful theory we've ever had in physics. Well, I don't know, maybe it is.
It is precisely tested theory in the paradigm in the history of physics?
It depends how you measure or what you mean by precisely tested. There are things in general relativity which are even more precisely tested. But you see, they're very limited. Quantum mechanics tests over a huge range, and that's certainly true. But the trouble with quantum mechanics is it's a self-inconsistent theory. It's got one procedure, which is the Schrödinger equation, or unitary evolution, or whatever you like to call it, which tells you how the state evolves continuously, smoothly in time. it's got the other part, which is what's called making a measurement. You look at the darn thing, and it does this or that. It doesn't do a superposition of this and that at the same time. That's called the collapse of the wave function, or the measurement problem, or something, and it's inconsistent with the Schrödinger equation. Lots of people struggle to make it consistent. If you do that, you're led into what's called the many worlds view. All these things do take place in different worlds.
So essentially, we absolutely all agree quantum mechanics is incomplete.
Inconsistent.
Nobody, and inconsistent.
You see, people were much too polite.
Yeah.
In these old days, Einstein was much too polite. He said, and Schrödinger, they were terribly polite. They said, quantum mechanics is incomplete.
Okay.
I'm being rude. And I say, quantum mechanics is inconsistent.
This
Self-inconsistent.
is an Oxford knighted professor being rude.
I'm being rude, yes. Well, it is rude.
Terribly rude.
Yeah.
It is inconsistent, but that's a well-accepted fact across
a lot
all
of people
physics.
don't. Yes.
Across all of physics, it's a well-accepted fact that quantum mechanics is inconsistent. So, but that's fascinating, but what does that have to do with consciousness? Why are you plugging, it's agreed, so, I mean, I know that you have been chastised for this, and I really think it's a low-level criticism, and I really don't want to advocate it, but people are like, consciousness is unknown, quantum mechanics is unknown, let's put them together, and I know that's not what you're doing, so I want to ask you to say why that's not what you're doing.
Well, because if computational systems, I'm trying to say, can't do understanding. I mean, that's the Gödel business. Now you see, is physics a computational system? Well, if it's Newtonian mechanics, it's pretty well a computational system. If it's general relativity, it's pretty well a computational system. If it's quantum mechanics in the sense of following the Schrödinger equation, it's pretty well a computational system. So we have to look for something in physics which has a chance of being not a computational system. Where do we see in physics something like that? The only place I can see is in the collapse of the wave function, because that is, you're cheating. You're going outside the computational system. I mean, it's not saying here we have a problem, here we have a problem, maybe they're the same. It's not saying that at all. That's what you're saying.
But you're essentially saying you believe, you're a physicalist.
Yeah.
You believe that the mind is physical, obviously, and that the structures that we've inherited to understand the mind come from the structure of the mind itself.
Yeah,
and so it's sort of this loop, and then you can say, well, where are the things that could possibly give us a hope of understanding something? And you're just doing your best guess, basically, because you do have conjectures in physics, but you're essentially known for really hardcore, unambiguous calculations. Like, I just also want to point out just before, because we're about to break for questions, but Hawking's Stephen Hawking is very famous for Hawking radiation, which is completely counterintuitive. And if Hawking had come out and said, black holes radiate, I can't really explain it, people would have freaked out. Nobody would have believed it. And you also simultaneously, concurrently, were proving that spinning black holes had a very similar process in what we now call the Penrose process, which was, these are basically ways that things that have no right to generate energy are making energy by exploiting the fact that energy is relative. And it's a very surreal phenomenon that you can spin down a black hole by creating Penrose radiation, that a black hole can evaporate by creating Hawking radiation. You and Hawking were really in there, man. You guys were really in there. But if you had not, I guess the point I'm trying to get to is that if you had not formally, mathematically proven it, nobody would have taken you seriously. And here you are, mathematically not proving it, really going out on a limb for you, being really kind of a maverick, just saying, I'm just conjecturing.
I don't think it's...
I can't prove it.
I think that's a bit of an unfair Well, I think you're agreeing with me. Really. A bit of an unfair criticism.
I'm giving you an opportunity to
Yes,
respond.
Sure. No, I understand that. No, you see, it's just, I'm looking for a place where the picture that we have of the world is fundamentally incomplete or inconsistent, in fact. And that's the only place that I can see clearly that is the case. And so if you're trying to find somewhere where a process could be non-computable, that's the best place to look.
Before I open it for questions, I really do want to ask, why can't non-computable processes be non-quantum? Why do they have to be quantum?
Well, I mean, what theory are you having? I mean, well, there are, I can give you an example of a non-computable process. Well, I'm not sure it is. It's a good example.
There are classical non-computable processes.
Well, there is one, which is actually due to Dirac, which is quite interesting. I wouldn't swear that it's non-computable. I think it probably is. Dirac, it's rather amazing because he had the equation of the electron, which is the Dirac equation, which is one of the most beautiful and exact theories we know, which describes how electrons behave. But he also toyed with ideas, classical models of particles, which could radiate, charged particles moving around each other and radiating. In order to make this work, there's a little problem with making, because they act on themselves, and that's the trouble. A charged particle, it's a little problem because the charge has to move into its own field as well, and so you have to have ways of getting rid of that. And he had ways of getting rid of that. And he produced this scheme where particles, the trouble was that there were too many solutions to the equations. Rather than being second order, they were third order. That's the technical point, but that was the thing. And what you found is that these charged particles running around, every now and again, they would start accelerating just by themselves. And they'd go shooting off faster and faster. And that's not something you want. So you had to restrict the solutions so they never did that. And then that was the kind of model. But the trouble is, how do you know they're never going to do that? Because they might, wait 100 years and then suddenly one of them does that. So it's basically a sort of non-computable problem because you don't know simply by computation if ultimately something goes shooting off, self-accelerate.
Yeah.
So I think it's an example of a non-computable classical situation.
Oh, that's an interesting.
Yeah.
That's very interesting. Sometimes I wonder if the entire universe is a non-computable classical problem. But before we open it up to questions, I just want to harken back to the time that you were working on black holes.
Yes.
And you probably weren't sure they were real at the time you were working on them. And here you are in 2019 working on consciousness. And there's got to be a part of you that's not sure.
I think consciousness is real, if that's what. Yes. Yes.
Honestly, I'm pretty sure I'm just imagining all you up.
Yes.
So are you...
I see. How confident am I about that?
How comfortable are you with the ideas of consciousness that you're
I think we're much further away. Sorry, I'm interrupting you again. I think we're much further away from an understanding. You see, the black holes we had a pretty good idea. I mean, a lot of things which, people had to work out complicated calculations about what they actually do in detail. But the general idea was pretty clear there. Whereas the issue of consciousness, first of all, it depends on a physics that we don't know yet, which is what really happens with the collapse of the wave function. And there are experiments. The longest standing one that I know of is by Dirk Bouwmeester, who is a Dutchman, who I've known for about 15, 20, I'm not quite sure when I've met him first, but he has designed an experiment where you put a little tiny mirror, is a mirror which is about 1/10 of the thickness of a human hair, it's a little cube actually, and it's just too small to see, but you hit it with a photon, which is beam split. Now what does that mean? You have a photon and it goes through a half-silvered mirror, which means part of the photon goes this way and part of it goes that way. You've got to believe that the photon is in two places at once. Quantum mechanics says, yes, it is, so you have to believe that. Okay, that's fine. May not seem fine, but it's fine. Okay,
doesn't seem fine.
The photon is doing these two things at once. Now, one of these beams, this this part of the photon's existence, you keep it in what's called a cavity. So you reflect it backwards and forwards, and it just keeps there. The other one, you have a funny kind of cavity, which consists of a mirror, which is a sort of hemisphere, and it hits this little tiny cube about 1 million times, backwards and forwards. And it pushes it in that just enough.
Photon pressure pushes it.
So that because the photon is here and here at the same time, it's pushing the little mirror and not pushing the mirror.
So the photon that's not there is pushing the mirror.
The mirror, yes. Well, the one that's not hitting the mirror isn't moving it.
Yeah.
So the mirror is moved and not moved at the same time. So it's a sort of Schrodinger's cat.
Mm-hmm.
It's in two places at once. Mm-hmm. Now, according to the scheme, which I put forward some while ago, you can, because of gravity effects on quantum mechanics, you can estimate a time scale for it to become one or the other. And that time scale, you'd like to say something like seconds to minutes. So I think that's the sort of, I'm not quite sure where the experiment is now, but it's pretty close to being done. And the thing is that you could tell whether this little mirror has become in one place or the other in seconds to minutes or whatever the criterion is. Depends on what its mass is and the distribution of particles in it and so on. But it's a pretty clear experiment. Now, according to standard quantum mechanics, it would never become one or the other. It would remain in two places at once. But according to the type of scheme which I'm putting forward, which is where gravity has to be taken into consideration, and this is the gravitational field of the little mirror, so it's a very tiny gravitational field. When you take that into consideration, you see there's a conflict with quantum mechanics. The very basis of general relativity, the principle of equivalence, which you talked about before, that principle is in conflict with the superposition principle of quantum mechanics. And so is this conflict really being shown up by the fact that this little tiny mirror becomes in one place or the other? And it's really exciting, because when I saw him last, which is in Vancouver at a conference, he was pretty well indicating that within 2 or 3 years, he'll have an answer to this, which is pretty consistent with his predictions. Because I was in Leiden, where his base, one of his bases, is Leiden and Santa Barbara in California. And he, at one point, quite spontaneously, without prompting, said, in 10 years, we'll have an answer. I saw him 2 years later, and he said 7 or 8 years, we'll have an answer. Then I saw him in Marseille, and then I saw him in Vancouver. And he's pretty consistent. He was saying, he dropped a year or two, but not much. He was saying, in 2 or 3 years, we'll have an answer. So I think he's probably right.
And does this remain the central focus of your interest?
One of
the
them?
issue of consciousness?
No.
Quantum mechanics, consciousness, quantum mechanics.
I don't think we're going to have an answer to consciousness for a long time.
So quantum mechanics you were just describing, do you feel...
You see,
which, like if you're a betting man...
I'm not.
You got your horses you got quantum mechanics in one stall.
Yes.
You have consciousness in the other. And I don't know, what do you have? Cyclic cosmology.
Other cosmology.
And the arrow of time. What are you betting on?
The cyclic cosmology first, because we already have pretty good evidence for that. People don't believe me. But that's because they haven't looked at the data.
So
there's really good evidence there. That one I think is number one. Number two is the quantum experiment. Maybe... There are other experiments. I have a colleague, Yvette Fuentes, who has an idea using Bose-Einstein constant. It's a very clever idea that maybe it works. And if so, it might be done quicker. I don't know. But anyway, in a few years, we might see that. So that's number two. Consciousness, way off. I don't think we're going to know for a long time.
Yeah.
But the ingredient that I consider to be necessary would be in this Baumeister experiment or something similar, to see whether quantum mechanics really does break down at that level. So
essentially, the underlying theory that you're looking for consciousness would also be the underlying theory for all the other things.
Well, it could be shown wrong, you see.
Yes,
yeah,
but if it works for consciousness, it works for everything.
I'm not sure about that.
On that note, on the note of uncertainty, I really want to open this up to questions, because we're pushing our audience to really late. But please, before we open it up to questions, let's take a moment to thank Sir Roger.
Well, thank you.